How's it going? Hello, Nookus. Good evening to you. I'm doing well. Having a good Monday. Hello, Death Scripts Pog. Off-topic question, but what's the music you play in the background? I kind of dig it. I think if you're watching this on your computer right now, I have a Twitch overlay, and it tells you what the music is that I'm playing right now. Let's see. It looks like, yeah, Vogd. Yeah, I have like this overlay. It's the Soundstripe app, the Synthwave playlist. Yeah. I dig the vibe of synthwave. Hello, Inca Deeb. Happy Monday evening to you. Have you guys noticed? It's 7 p.m. and the sun is still bright and shining. Isn't that magnificent? Hello, Flowers of Algernon. It's a beautiful thing. The time shift messed up my schedule a bit though. Yeah, agreed. It's always harder to like lose some sleep, but it feels good to see the sun again. I'm happy about that. Oh my gosh, it's that guy who stinks. Hey there, hello. Oh man. I hope you guys are doing well tonight. So we're just going to talk about assignment 1 a little bit. It's pretty fun. All right, I'm going to go over here for a little bit to explain the idea. So we have in our kit a DC motor, and it has proven to be troublesome. Because it kind of easily disconnects, has trouble connecting and whatnot. So what I want to do, we know that when we provide voltage to this motor, as an output, we get, among a couple things, we could say one of our outputs is angular velocity. And the way we provided different voltages is we used different duty cycles. So you could have 0 to 100% duty cycle. And that corresponds, because we were using a 5-volt source. So that's like 0 to 5 volts. And what happens when you provide a voltage to our motor, if you were to plot the angular velocity as a function of time. So we'll have angular velocity on the vertical axis, and then we'll have time. It kind of spins up pretty quick, and then it levels out. And we'll call this speed that it reaches the steady state angular velocity. And so for different voltages that you give to the motor, it reaches a different steady state angular velocity. So like for example, this could be the steady state angular velocity when 5 volts is applied. So that'd be like our maximum angular velocity. So if we apply less voltage, maybe 3 volts, then we should expect a slower angular velocity. Maybe it does something like this. I'm just kind of making this up. So maybe that's at 3 volts. So you can create a calibration relationship like this, where we have angular velocity on this axis, and we have duty cycle, which is proportional to voltage, on the horizontal axis. And so let's put a couple duty cycles on here, like 10%, 20%, 30. Actually, I'm going to run out of room here. 40, 50, 60, 70, 80, 90, 100. So this is our duty cycle percent. Now we know that, I don't know how much you guys played with the motor, but if you have a duty cycle lower than like 50%, maybe as you get towards 40%, the thing doesn't even really spin. So like if you put 10% duty cycle on here, the angular velocity it's going to be 0. This thing's not going to spin. And let's assume that happens all the way up to 30, and it's only once we get to like 40% duty cycle that we actually get some steady state angular velocity to actually happen. So what you're going to find is for most DC motors, once you get the motor spinning, there's a linear relationship between steady state angular velocity, and that's what I should put here. To be specific, I'm talking about the steady state angular velocity once the motor's spun up a little bit. If you measure that speed, it's going to kind of be a linear relationship. So I'm just going to try to draw a line that's steadily increasing here. And you could fit this data with a line. It's a linear relationship. You could fit it with a line. And this line, it's going to have a formula like y equals mx plus b, where the x variable, the horizontal axis, is duty cycle. And the y-axis is your steady state angular velocity. Now the cool thing about this equation, once you have it, is let's say I want to spin this motor at 2500 RPM. All right. Let's say I want 2500 RPM. So maybe that's over here or something. I want a steady state angular velocity of 2500 RPM. Well, with this line, I could bring this over and then go down and figure out what duty cycle I need. Maybe I need 72%. So if I want 2500 RPM, once I have this equation, it's going to be mx plus b, and I can solve for the duty cycle x. So like the duty cycle I need at 2500 RPM is 2500 minus b divided by m. So that's the power of having an equation like this. With this motor, I can choose any RPM I want, and I know what duty cycle to give. All right, so that's the big picture purpose of having a relationship like this. So you might have different industrial settings where it's like, hey, we need this lathe to spin at a certain RPM. So you could then, using this, you could write a code that sends the proper voltage to give a specific RPM for that lathe. That's just an example. All right, so if we want to build this calibration relationship, that you need some way of measuring the angular velocity of the motor. And here's our motor. As you can see, the only thing coming off of this, we just have our 2 voltage leads. And if you want to measure angular velocity of a motor, there's a couple ways to do it. Like typically you have what's called a rotary encoder, and there's a couple different types of that, but one type is like an optical encoder where it might be at the bottom of the motor, and as the shaft rotates, they have basically like a beam of light that shoots through a fan in a way, and they can count how fast the thing is spinning. That's like a simple explanation of a rotary encoder. There's nothing like that on here. There's no way to measure the angular velocity. So what we're gonna do instead, I actually saw this on YouTube. You can just put like a little piece of tape on here, and we're gonna spin up the motor, and then we're gonna record the sound. At different duty cycles, we're gonna record the sound, and then we're gonna analyze that sound file afterwards and figure out how fast it was spinning at each duty cycle. And then, if we know how fast it was spinning at each duty cycle, we can build a graph like this, and we can get the calibration equation. So that is what we're going to do. So how about we record some sound? Let's record some sound. Did you guys know that through UB, you can download the sound recording app Audacity, which is free anyways, so it's not like you really need to download it through UB, but okay. So this is Audacity right here, and these are sound files that I recorded earlier, but we'll record one live here. Thanks, UB. Okay, so this is our sample code for the motor, and how about we do, let's test 60% duty cycle first. So I'm going to set the duty cycle to 0.6, and then in the code, I just pick a direction, and then I write this. Any recommendations to prevent the motor wires from breaking off? Hey, it's hard for me to give advice because I broke the wires off my motor, and I was pretty gentle with it. So I guess if you're just a very careful person, but It's really not your fault. It's just that the solder connection on here is pretty weak. Okay, so I'm going to upload this code. For the homework, do we have to use the motor in our kit? Okay, yeah. So for this homework, I'm giving you all the data. You do not need to collect this data yourself. So if your motor is broken, don't worry about it. Don't even worry about it. You're not going to need that. Drulish says, I've broken about 10 leads in pins so far. My fingers are just fat. Brutal. Treat it like a newborn baby. That is good advice. That is good advice. If we just respected this motor like we would a newborn baby, then we wouldn't have this problem. All right, let's just test this. I'm going to spin this up. This is 60% duty cycle. Would I be able to resolder my DC motor connections? No, you definitely could. That's probably the best way to do it. I didn't suggest it because most of us just don't have access to that. Okay, let's open up Audacity. And what I'm going to do, I'm going to make a new track. A new mono track. And this is kind of fun because you can select the sampling rate. So like a standard sampling rate is 44 kilohertz for music. That's 44,000 samples per second. So that's how many samples per second we're going to be recording from this here motor. Let's make sure I got this running again. It doesn't really want to spin for me right now. Come on. Okay, good. Let's start recording a new track. Okay, and then we'll stop. And let's turn off, I mean, as much as it pains me to do it, we have to turn off the synthwave jams for a second. Let's play this back. It looks like it's going to be kind of soft. Can you faintly hear that? Okay, what I'm going to do, first I'm going to cut off this stuff at the end. Oh no, I did the wrong. Okay, track. How do I cut again? I think it was like Control-Shift-I. No, Shift-I, Control-I. Yeah, there we go. So I'm going to get rid of this. You enjoyed the strange audio files? Yeah, there's something else. Okay, so what I'm going to do is I'm going to go to Effects, and I'm going to amplify this. Okay, you see it's been amplified. Let's play it back now. Okay, that's the motor. You can hear it now. You could hear me breathing creepily at the end. Okay, let's chop that. Delete that. Chop that. DC motor ASMR. Basically. That's not bad. I could sell this as like white noise that people fall asleep to. It sounds like just like a fan or something. Oh my gosh, that guy who does not stink and that guy who does stink are in the chat at the same time. I don't know what to do about this. Okay, now look at this. Look at this. Actually, so I recorded all this in right here. So this is how I did it. But the MATLAB code imports these .wave files. So how about I'm sorry, I couldn't fall asleep to that. What, you don't like white noise? That is like pure gold white noise right there. So, I don't know if you know, well, now you know this, but MATLAB can load audio files, and it can also play back your audio files. You could load music into here. You don't just have to load motor sounds. So let's run this code. It's going to play back the audio. And here is, Estes is a white noise dealer. That's right. That's right. And if you zoom in, you notice that this is periodic. And each period here represents one rotation of the motor. I'm not sure what this little dip corresponds to. Wait, MATLAB plots audio? Yes. You can try it. Like, just take any, like, I think it can load MP3s. I mean, it definitely loads .wave. But yeah, for sure, you can load in audio, and it'll play it back. You can do sound processing, whatever you want to do. So I'm not sure. So I can put mixtapes on. You can make your own mixtapes on MATLAB. That's what I'm telling you. I've actually done some sound processing as an example. You're asking for a friend. You're not interested? Okay. Of course you're not. So we have this piece of tape on the motor, and it's turning around, and it's whipping towards the microphone at some point, and then it's like rotating away. And I don't know. I'm guessing this like dip right here is right when the piece of tape passes in front of the microphone. That's just my guess. Because the microphone is reacting to the pressure wave, the little pressure wave from that rotation at each point. So I think like this little dip is each time the piece of tape passes. Why is it negative? I don't know. Eric says, when I use the zoom in tool, it does not look as clean as yours. What exactly am I doing wrong? Well, what do you mean it doesn't look as clean? Are you loading in, like this one is the 60% duty cycle. There's different sound files that we have. It looks like a bunch of straight lines. What if you zoom in more? Or maybe you zoomed in too much? Oh, it's kind of hard to explain. You could shoot me a screenshot in the Discord. I could take a peek. Make your X limits smaller. So, what you want to do when you open the sound file, remember, we want to find out the angular velocity. So, the distance between two of these peaks represents one turn of the motor. So this means that one turn is happening over, let's see, what's the time here? This is 1.089 seconds over here. And this is 1.06 seconds. So it's like 0.02 seconds that it takes one turn. So from that, the angular velocity is the rotational displacement over time. So you have one revolution over basically 0.02 seconds. So that gives you the revolutions per second. but I want you to give me the angular velocity in RPM. So you're going to have to do a couple calculations in there. And so you're going to notice, like from the sound files, each of these is going to be a little bit different. And you can listen. This is interesting. The tone of the note is going to change. So let's start with 100% and work our way down. So as you get slower duty cycle, the notes get more and more bassy. 50% duty cycle is like a deep bass. %, 70. If these audio files were longer, we could make a little song by just switching between these. Somebody should make a mix in MATLAB. You could splice together excerpts from each of the sound files. Just concatenate the vectors together for specific time increments, and you could make a song. You would get so much cred for making a song. Okay. So I just want to show you one more thing. Like this is pretty brief what we're doing tonight. So what you're gonna do, let's go back here. So we have, I think it's, I'm not sure how many sound files, but it starts at 40% duty cycle, 50, 60, 70, 80, 90, 100. And you're going to have to determine the angular velocity in RPM for each one. And you're going to find that it's going to increase with a general trend like this. And it's going to be pretty linear. So once you analyze each of these and determine the RPM, your goal is to fit this with a line. And so I'm just going to show you really quick how to do that in MATLAB. Okay, so we want to like fit it with a line. So I'm going to go back to MATLAB and I'm going to make up some data. All right, we're going to say my X is, we'll just do 40, 50, 60, 70, 80, 90, 100. So this is X. And then I'm just going to make up something. In fact, I'm going to make it random. Random size X. What is that going to do? But let's make these numbers bigger. No, I don't want to do that. I don't want it to be totally random. I want it to be something like a line. So I'm going to say Y is like 1,000 times X plus 200. But I don't want it to be a perfect line. I want it to look kind of janky. So I'm going to say Y is Y plus some random noise. I'm going to see how this works. Times rand size Y. I don't know if this is going to work. Marker size 16. Let's make this plot. Well, okay. So something like this. So when you do your analysis, when you plot duty cycle on the x-axis and angular velocity and RPM on the y-axis, it may not look as nice as this. But we still want to fit it with a line. So I'm going to show you I'm going to show you the polyfit command first. Okay. So what polyfit does, it fits a set of data with a polynomial, and you get to pick the order of the polynomial. So a linear fit is a first order polynomial. So what you do is you say, I want to fit x, y with a first order polynomial. So the first argument is the horizontal axis data. So that's going to be duty cycle. Y is the vertical axis data, which is going to be angular velocity in RPM. And then first order polynomial. So if you just run this command, it's going to give you back two numbers in this case. Okay, what are these two numbers? Let's go back over here really quick. Those two numbers, so our polynomial is like y equals, well, this is our polynomial. It's a first order polynomial, mx plus b, right? Yeah. So the first number is m, the slope. The second number is b. And if you do higher order polynomials, then the first number will always be the highest power. Like, so your first number would be the x squared, and then the x, and then that. So if I did a second order polynomial, a quadratic polynomial, it would give me three numbers. First number, second number, third number. But we're only doing a first order polynomial, so it's two. So it's those two numbers. So what I'm going to do is I'm going to say like my linear fit is, oh wait, we need to store these two numbers in a variable. So what I like to do, I like to say like my polynomial is that. And then my like line, because I want to take these two numbers and make a line out of it, it's going to be, I take the first number and I multiply it by x. And then I take the second number, which is my like intercept. And this is going to return the line itself. So now what I'm going to do, I'm going to make a new figure. I'm going to plot the original XY data and have like dots connecting them. But then I'm going to plot X, and I'm going to plot my line, and I'm going to have like a red line going through it. So now this will have the data, and it'll also have my linear fit of the data. And there it is. And the dots are really small, so you kind of have trouble seeing them. But that's how you use polyfit to generate a line. Okay, I'm going to show you another way to generate a fit. What you can do, you can go to Tools. Like once you have a plot that you want to fit, you go to Tools, you go to Basic Fitting, and then it gives you, it gives you these options. And you can pick the type of fit that you want. And there's an option that says linear. And what it does is it runs the polyfit command, and then it just automatically throws the line on top. And it also adds it to the legend. And you can click on Show Equation, and it'll put the equation of the line right on top. And then you can just close it after. So that's another way to do it. That's the lazy man's way of generating a fit. Actually, I won't say that. There's both ways have their utility. Sometimes you want to just automate fitting data with a line, and that's when you use polyfit. And sometimes you're just doing like one fit, and it's quick to just, okay, do it yourself, click a couple options. But if you had to fit tons and tons of data, you wouldn't one by one pull up a plot and do a fit. So it's good to have both of these options available to you. So Okay, you're going to have duty cycle, you're going to have angular velocity, you fit it with a line, and that's your calibration relationship. And remember, the reason you want that calibration relationship for a motor is so you can go back and be like, yo, I want to spin this at 2500 RPM. What duty cycle do I need to plug in? Well, you go back to this equation and you solve for the duty cycle that you need. And I think this is fun because it's like, it's a non-traditional way of measuring the angular velocity of a motor. And it worked out pretty nice. And we got some nice ASMR sounds out of it. For A 1.1, are we supposed to show our work with the screen capture of the MATLAB? Okay, so A 1.1, let me pull that up. So this is the assignment document. 1.1. For each duty cycle, zoom in on the signal and determine the period of oscillation. You don't have to, yeah, I see what you're saying. I think it's a good idea to show a screenshot of one case like I did here. But then just fill in the table afterwards. You don't have to show it for everything. I think it's good practice to like show as much work as possible when you do a homework assignment, just so it's all recorded. But I realize it could be a little tedious doing a screenshot for everything. So maybe just do one example one and be like, this is how I'm doing it. Like you don't have to, like the way I did it is I was measuring between these 2 points, but it could be really any place within the cycle. Quick question, says Tommy. When you say the assignment needs to be typed, what really needs to be typed? Seems like everything would be tabulated, plotted, and calculated in MATLAB, and maybe the table's prettied up in Excel. Can we just publish our code with everything calculated, and then maybe fprintf? I'll leave it up to you. So, the reason I want it typed is number one, so it's neat, and kind of like uniformly formatted. I also wanted it typed so that all the MATLAB code can easily be thrown in an appendix, and we just have one PDF that we look through. Because there's so many students in the class, it can be graded faster the more uniform all of the assignments are across every student. So I'm trying to like make the format as uniform as I can, just so it's easier for everybody to get feedback on it. So can you just publish your code with everything calculated in the... Yeah, if you like make an fprintf command that makes these tables pretty quickly, and gets everything in there, that's totally fine with me. What other questions do you guys have? Yeah, no problem, Tommy. Is it okay if we use Excel to make the table for part? No, I'm just going to say no Excel for anything. Don't you even dare. I realize it's trivially different between making like this table in Word or Excel, but I just I don't want there to be any confusion here. Like, this assignment is to be done in MATLAB using MATLAB tools. The only other software we're using is like a word processing software to just organize those MATLAB results. MATLAB all day. Yeah. We're just practicing more and more, and it's really not so bad. It really isn't. So it's okay if we make the table in Word. Yes, that's okay. That's okay. I mean, you You do all of the actual analysis, the curve fitting, all of that in MATLAB. And then when you're just typing up the results, you can format like a table in Word. That's okay. Look up the table function in MATLAB documentation. It's actually really easy and fast if you already have... Ooh! Hey, thank you for that. I actually used the table command like for the first time pretty recently. And your Google how to make a table in MATLAB. It's a beautiful thing. Yeah, it's pretty sweet. It'll organize everything for you. Huh. Yeah. Yeah, if you ever have questions about MATLAB, their documentation is pretty sweet, and they always have a couple examples in there, some sample code and stuff. All right, everybody, that's it for tonight. I just wanted to walk through that assignment. You can always come back to this video and refresh what's going on. I appreciate you guys, all your hard work. We're almost like halfway through the semester, you know. Believe it or not. The days are getting brighter. They're getting longer day by day. Springtime is almost sprung. All right, everyone. Have a fantastic night. Peace.